Okay, we have another integrating factor method of solving differential equations problem. So I'm going to go through the steps again. Calculate the integrating factor I of x equals e to the integral of p of x dx. You need to get it in the certain form. Remember, this is directly from your formula book. If you can get a differential equation in this form, then you're in a position to use the integrating factor method. So you calculate the integrating factor, you multiply through by it, then you use sort of intuitive steps to massively simplify the left-hand side, then you integrate, and then you're probably going to do something else to make the integration actually simple on the right-hand side. And then you're in a position to get a general solution, get a particular solution. In this case, we want a particular solution. We are given initial values, which makes it an initial value problem. So the question says, solve the initial value problem, cos x dy by dx equals y sine x plus sine of 2x, and the initial values are y of 0 equals 1. So that means when x equals 0, y is 1. So that is a point on the curve. When it says solve, it means give a function of y in terms of x, right? Or in this case, it's y in terms of x. It doesn't necessarily have to be y and x, but you're going from a differential equation to an actual equation with y as the subject in this case. Right, so you can see we've got some issues. So we want it in this form where we've got y dashed, which means dy by dx plus p of x times y equals q of x. So what we have is we've got a y dashed here, but then we've got an issue here. We don't want that because to apply this method, you want the y dashed on its own. So that cosine x has got to go, right? So that's the first thing. So we have cosine x dy by dx equals y sine x plus sine of 2x. So there's a couple of other issues as well, but let's just start on the cosine x. So we're going to start by dividing through by cosine x. So that is going to say dy by dx equals, so we've already divided the first term by cosine x. The next one's going to be y sine x over cos x. Over cos x plus sine 2x over cos x. So we've just divided through it by cos x. So we're getting closer. So we now have dy by dx equals something, but we want it to be dy by dx plus p of xy. And then we just want a function of x. So our p of x is going to be this sine over cos, which we can call tan. But keep bearing in mind that we've got to integrate it. It's actually a lot easier to integrate if you call it sine over cos. So I'm going to leave that, but I am going to move it onto the other side. Right, so when we do that, we're going to have dy by dx minus sine x over cos xy y equals sine 2x over cos x. Okay, so we want to simplify it as much as we can. We're actually doing quite well with regard to the integrating factor. We've got our y dashed, yes, plus p of xy. Well, the p of x can be minus sine x over cos x times y. That's something that we should be able to integrate if we get a u substitution involved. Equals another function of x. So we've already got it in the form that we want, but we can just simplify this right-hand side a little bit. So the more you can simplify it, the better. So dy by dx minus sine x over cos xy equals, or sine 2x, a double angle identity. There's only one for sine 2x. It's 2 sine x cos x. So that's over the cos x. And those cosine x's, we can cancel those out, 1, 1. So now our differential equation in the form that we can use the integrating factor method for is dy by dx is dy by dx minus sine x over cos x y equals 2 sine x. Okay, so just to say again, dy by dx is our y dashed, p of xy is our minus sine x cos x y, and q of x is our 2 sine x, right? So the integrating factor is e to the integral of p of x dx. So we need to integrate p of x with respect to x, and p of x is minus sine x over cos x. So like I say, you can call that minus tan x, but to actually integrate it is much more useful in that form. So the integral of p of x dx, well, that is the integral of minus sine x over cos x dx, which we could write as minus the integral of sine x over cos x dx. So the way to go about this is to use a u substitution, which is going to knock out that numerator. So we're going to let u equal cosine x. So let u equal cos x, which would mean du by dx equals minus sine x. So it's even going to knock the negative out as well, which means that du equals minus sine x dx. dx equals du by minus sine x. Okay, so now we can completely transform our integral of p of x dx. So now the integral of p of x dx equals the minus that we already had, minus 1 times the integral of, well, it's sine x over u, cos x is u, times du by minus sine x. Okay, so looking at that, well, the minus signs cancel each other out, very friendly, and so do the sine x's, 1, 1. So we're just left with the integral of 1 over u du equals the integral of 1 over u du equals ln u. Remember, for the integrating factor, we don't need to worry about a constant of integration. So it's ln of the absolute value of u equals ln of the absolute value of cosine x. Right, so back to our integrating factor method. We have calculated the integrating factor. Well, we haven't actually. We've calculated the integral of p of x dx. The integrating factor is e to the result of that. So I of x equals e to the power of ln cos x, the absolute value of cos x. ln of x, so ln of cos x is the power you raise e to get cos x. So then if I raise e to that power, it's just going to be cos x. So actually the integrating factor is cos x, which is hopefully going to make things really nice for us. Okay, so we've got our integrating factor, no constant of integration required. Now we can multiply the differential equation through by our I of x, which is cos x. Okay, so the differential equation that we need to multiply through by the integrating factor is dy by dx minus sine x over cos xy equals 2 sine x. dy by dx minus sine x over cos xy equals 2 sine x. And remember, we need to multiply through by cos x, the integrating factor. So once we do that, we're going to have cos x dy by dx minus, well, sine x over cos x times cos x is just sine x, so minus sine x times y equals 2 sine x cos x, which potentially we might need to write as sine 2x later on. Okay, so now we're into the bit where we look at that left-hand side and we see if we can identify a reverse product rule so we can express it as a derivative, okay? So simplify the left-hand side, we're looking to obtain the integrating factor of x times y equals the integral of the right-hand side. So we're basically hoping that all of this left-hand side is the derivative with respect to x of the integrating factor, which was cos x, times y. And we can check that. If you thought about the product rule, let's just check if that is true. Okay, so if you wanted to differentiate cos xy, you'd have your u and your u dashed, and your v and your v dashed, and they would be as follows. So you'd have your cos x as u, and u dash would be minus sine x. V we said was y, so dv by dx would be dy by dx. Okay, so if we wanted to write that in the form of so u dv plus v du, so u v dashed plus u dashed v, that is going to be cos x times v dashed was dy by dx, plus u dashed v, which is minus sine x y. So we can see that it is indeed true. So once you get to the bit where you've multiplied through by the integrating factor, it's always going to be the derivative with respect to x of the integrating factor times y. That is the whole reason why the method exists. Okay, so at this right-hand side, I am going to call that sine 2x because I'm going to have to integrate it very soon. Okay, so now we are ready to integrate both sides with respect to x. So if we just integrate that left-hand side, we're just undoing that derivative. So that's just going to be cos xy or y cos x. So y cos x equals the integral of sine 2x dx. Okay, so that is quite a friendly integral. So you could get a u involved and do the whole thing, or if you've done enough of these, you should know it's going to be minus a half cos 2x. So this is minus a half cos 2x plus the constant of integration. Okay, so if you just think about it in reverse, as in if I differentiated, if you think about minus cos 2x, if I differentiated that, that would get me 2 sine 2x. So I'm going to need the half to make sure I only get 1 sine 2x. And that is y cos x. So now for a general solution, I can divide through by cos x. So y equals, y could be written as, if we keep the 2 on the bottom, we're going to divide by cos x. So we're going to have a 2 cos x on the bottom. On the top, you've got minus cos 2x plus c, which you could call c minus cos 2x. I don't like to start with a negative. Okay, so that is the general solution. We have been asked to solve an initial value problem. Okay, so we need to now substitute in when x equals 0, y equals 1. So at 0, 1 equals c minus cos 2 times 0, so just cos 0, which is 1, over 2 cos 0. Cos 0 just equals 1, so 1 equals c minus 1 over 2 times 1, which is 2. So 2 equals c minus 1. 2 equals c minus 1, so c must equal 3. So the particular solution, the solution to the initial value problem, is going to be y equals 3 minus cos 2x over 2 cos x. Okay, so it's not the most satisfying final solution, asking to be simplified, but actually you're not going to make it look any better than that.